and going on to our keynote speaker. Just a second. Our keynote speaker today is Mr. Avishai Shalom. You may probably know Avishai from the community. He's been quite of a veteran here in the community. Avishai is, I've known Avishai for over 10 years when he founded his consultancy firm back in Few Bytes, and since then he's done so much around as engineering in residence in a VC and engineering manager at Wix and so much more. So lots of adventures, and now he's converted to the dark side, being a developer advocate at Scylla. If you know the Scylla DB open source. Let me add Avishai to the stream. Hey Avishai, good morning.
Good morning, how are you?
Great. How are you doing?
Great, it's been a while.
yeah. Since the last time I hosted you on a podcast.
Yeah.
So, Avishai, we've been around for a while now, and without saying our ages, and we've seen so many transformations in the IT. From on-prem all the way to cloud and serverless, from pets to cattle, from 3-tier apps to microservices, Death Star. So, how would you say this impacts our choices, our assumptions? What's your take on that?
So the problem is that technology moves really fast, but our brains don't move as fast. There's a lot of stuff that we're conditioned for, and patterns in which we think, and we tend to take them away and kind of pattern match even on things that are not exactly the same. And the other problem is that because of the organizational structure of the technology community, be it protocols or projects or whatever, actually getting people to agree on how to use stuff is very, very hard and takes a lot of time. So a protocol to make it ubiquitous takes about 30 years, which is, if you think about it in terms of hardware, it's eternity. So we have a lot of protocols which are not suitable for the way we use them today. So like a very good example would be telephone lines. A lot of us here in Israel use ADSL lines. And then if you still have a phone at home, you're basically using a phone emulation on top of some kind of a compatibility layer on top of actual phone lines.
Yeah.
And the entire world is like this. It's not only phones. That's
let's leave some teasers for the talk itself, because I think you're touching some of these. So I'll just roll it over, and for our viewers, participants, do ask away questions for Avishai. He will answer Q&A after the talk, and you also come back to us after the talk itself and to answer some of the questions. So do ask away on Discord, and Avishai will try and answer at least some of these questions after the talk. So see you again, Avishai, after the talk. Good luck.
First, a word from our sponsors. Are you using QWERTY? Having trouble reading that email? A4-size documents aren't readable on your phone. If you're suffering from any of these symptoms, you might be experiencing obsolete design. Consult your doctor now. Welcome to The World Has Changed, Have Our Designs. My name is Avishai Shalom. I'm Nuckenberg on Twitter. You can find me there. Follow me if you like. I work for a company called Scylla. We make a database, a distributed database, high performance, that's compatible with DynamoDB and Cassandra. Look it up. It's very interesting. It's open source. You might like it. So why are we having this conversation? The problem is that our brains are programmed for familiar patterns. And when we look at the world, we see those familiar patterns, even when those patterns are no longer relevant, because the world has changed around us. Hardware has changed dramatically in the last 30 years. Use cases have changed dramatically over the last 30 years, but sometimes our systems have not followed suit and have not changed accordingly. So I'm going to give a few examples of this. But before we dive into those examples, we should probably take a look at this table of latency numbers that every developer should know. There's a very interesting and famous table out on the internet. Look it up. You can find it on GitHub. But I'm going to run through it very, very fast. So magnetic disk, random SIC takes about 10 milliseconds. SSD is about 50 microseconds. Round trip in the local area network in data center is less than half a millisecond, sometimes about around a quarter of a millisecond. To read from SSD 1 megabyte is about 1 millisecond, and to send 1 megabyte over a network is about 10 milliseconds. Now, let's dive into those examples. Let's talk about Hadoop. Hadoop is an open source project that's basically a framework for processing big data. It was originally open sourced by Yahoo in 2006, but it's based on a design from Google from 2003, 2004. The MapReduce and GFS papers, very interesting read. It was later picked up by Cloudera and later Hortonworks for further design and to popularize it in organizations around the world. Amazon later in 2009 provided the service, Hadoop as a service, EMR, which was basically on running Hadoop on EC2. And around 2013, this was where Hadoop started being widely adopted in enterprises and corporations. So about 10 years that took from when Hadoop was originally designed until it was adopted in many companies. So what was the design of Hadoop? What was it based on? So basically, we're talking about big data, so a lot of data, much more data than you could store in a single machine. So we needed a lot of machines. This was why it was distributed, and those machines used commodity disks, magnetic disks. And because RAM was expensive, we actually had much more data than we had RAM. So basically, Hadoop was a framework that needed to work off the disk. Network bandwidth was also fairly limited, so we couldn't really move data between machines very easily. Also, this was designed for physical networks, so we actually cared about the topology of the network for locality. And we're talking about very large files and data sets because this is basically what big data is. All of those conditions brought forth a design rationale that was based around data locality, which means we want to move data only when we really, really need to. We don't want to move data if we don't have to. How do we do this? We move the computation to the data. But if we look at the differences that happened between 2003 and 10 years later, a lot of things changed when we're talking about hardware. For example, the network bandwidth was almost 10 times as big. Disks, although they didn't become much faster, they have become much, much larger. And similarly, RAM has become much bigger as well. Also, we now had SSD, new storage technologies. SSD became commonplace, and also virtualization. We were no longer talking about physical networks and physical machines. For example, EMR was natively based on the cloud, so everything there was virtual. If we're talking about RAM prices, it's worth taking a look at this very interesting graph. This is a graph of RAM prices from the early 2000s till more or less today. And I actually have data all the way from the 50s, but because the RAM prices drop exponentially, if I actually put a graph that dates back all the way to the 60s or 50s, you wouldn't even see this part of the graph because it would look like a flat line. So RAM prices drop exponentially, the size increases exponentially, and this is expected to continue. And in 2013, it actually became very, very obvious that this is going to be a trend that's going to continue. So let's revisit the design assumptions that we had. Data is still larger than RAM, but we actually have much more RAM. This ratio was not as extreme as it was before. RAM has become much cheaper. The disks were no longer necessarily magnetic. The network bandwidth was no longer limited relative to the size of the data. We still had large files and large data sets, of course. But when we're talking about this kind of system, where we have much more RAM and much more bandwidth, it now makes sense to move data from the disks to the RAM of remote machines and process it there where the computation is. So we actually had a new design that made more sense, and by 2013, everyone started to move from Hadoop MapReduce to newer, more modern frameworks that were based on newer designs, Impala, Spark, Presto, and things like that. So by the time Hadoop started being widely adopted, it was already deprecated. This happened in less than a decade. So now let's talk about something really, really old, relational databases. Relational databases are about 30 years old, if not more. Oracle, for example, was initially released at the end of the 70s, MS SQL, end of the 80s. Postgres and MySQL were released mid-90s, but the design is actually based on older projects from the 80s. So relational database design is actually more than 30 years old. What was the design rationale of relational databases? The design rationale was based on the fact that RAM was small and super expensive, and also disks were, especially fast disks, were very, very expensive. So if you think about the fact that when you need to look for something in an index, you need to do a few disk seeks. So let's say you do about 5, it takes about 50 milliseconds to find something in a disk-based index. But if you're actually looking in RAM, it's much faster, and if the network round trip is around 1 millisecond, it actually makes more sense to fetch data from a remote server that might have the data in RAM than it is to do local disk seeks. It's much, much slower. So what do? We send the computation over the network to where the data is hosted on a big monolithic server that has a lot of RAM and a lot of disks and is likely to have the data, or at least the index keys, cached in RAM. This brings us to this kind of architecture, which is the famous 3-tier architecture. This is just the bottom 2 tiers. The database and application servers. So we have a bunch of applications which are stateless, and they store all the state in the database, this big monolithic expensive database. And every time they need to do something, they talk to that database, they send a query, RPC style, they get a response, and they do their computations. But when we fast forward to 2020, a lot of things have changed. We now have SSD drives, which are much, much faster. The latency is about 50 microseconds. RAM has become much cheaper, and so has SSD. Network latency hasn't changed much, but the bandwidth has grown about 100 times. So does that change anything? Actually, it does. Now, it's actually cheaper to fetch data from your local disk than it is to go to a remote server. It's about, let's say, 200 milliseconds or 250 microseconds to get data from a disk-based index on your local SSD, and it's about 1 millisecond to get the data from a remote server, even if that server is very big and very powerful. So the rationale has changed dramatically. And if we think about this, we actually arrive to architectures like this, where the application servers keep a replicated copy of the database locally. So in many machines today on Amazon, we actually have a lot more RAM and local SSD than we use. Many applications don't actually use the local data and local disk that they get for free. In Amazon, in many instances, you get terabytes of free NVMe storage, which is very fast. And if we want to utilize it, we need to store data locally. And this is basically what this architecture does. It uses network replication to utilize the high throughput of the network, instead of being latency bound by doing repeated RPC calls. Another example is the common cache architecture. So usually we would have a centralized cache, usually Memcached or Redis or something like that, and all application servers would go remotely to that cache server to fetch data. The downside of this architecture is that if you need to spend 1 or 2 milliseconds to get over the network to the remote cache server, that sometimes is less efficient than just going to the database. For example, the database could deliver a response in the same time frame, so you're not actually saving time by going to the cache. If, of course, you have a cache miss, then you also have to go to the relational database and you're actually doubling your latency. So given the hardware that we have, it now makes sense to have this kind of architecture where you have cache replicas reside locally on application instances. The SIC to the local cache is very, very fast, almost 0 time. And because we have, in many cases, especially in Amazon, we have fast NVMe drives on application servers, which are sometimes very big and currently not being utilized, we can actually use them to store cache very cheaply. Or in RAM, it's not uncommon to see machines in Amazon that have several gigabytes of RAM which are not being used by the application. So again, we can replicate from the database and utilize the high throughput that we have over the network. And this is what some innovative projects do. There's a project by Google called Group Cache, for example, which has local cache, local RAM cache on application servers and basically replicates from peers. Also very interesting. I recommend that you look at it. Let's talk about relational database clusters. So relational database cluster is basically a cluster where you have a primary which has some kind of transaction log or write-ahead log, which is the basis of replication. The secondaries read this log and apply it on the secondaries, and that log is persisted on all the servers, both the primary and the secondary. And for persistence, on every machine, we basically write twice, right? Once to the log, and again to the, you can call it a snapshot, the data file of the database. This design has a very clear rationale. The clear rationale at the time was that we need to make sure the data is durable. This is the D in ACID. And we also need to make sure that writes are atomic and consistent and isolated. Data loss is not acceptable because if something happens to the disk, we need to be able to recover it. Not necessarily we have a replica. Back in the day, 30 years ago, you sometimes have only one server. Downtime was acceptable, but data loss was not acceptable. And all of this design basically assumed that you have very reliable physical hardware. So there's a lot of code in database, in a relational database, whose goal is to make sure that if you get, if a write gets acknowledged, that means it's safely stored on the disk, and even something bad happens to the server, you can still recover that write, that data from the disk. Might be with forensics. So for example, you could send the disk to forensics and recover the data from there. But this kind of assumed that we have physical hardware and monolithic servers. What happens when in the cloud? Today we run servers in the cloud. It's not possible to get the physical disk for forensic from Amazon. That's not going to happen. Also, today we need uptime. So we're no longer willing to tolerate downtime. So if we have a problem with the database server, we're going to fail over to the secondary. And when we fail over to the secondary, it doesn't matter if the data that we've written has reached the disk on the primary. If it's not on the secondary, we have lost data. So having this kind of durability and ACID guarantees doesn't actually help us anymore because we can't actually utilize it. So this is the common architecture that we have in the cloud. We basically have two nodes, a primary and a secondary, and we write the disk. The disk is usually EBS, that's a persistent disk on Amazon, and EBS is a network disk. It's a remote storage, and underlying inside of the EBS stack, it's basically replicating to 3 different storage nodes. So we actually have 2 layers of replication, one for the database layer and another for the storage layer. So that means we basically have a replication amplification. We replicate many more times than we planned for. But this also means that we don't actually know what's the actual durability of the data is. Why? Because the fsync, the system call that's supposedly has semantics of, if this is acknowledged and this is safely on the disk, it's now virtualized. So we don't actually know if it gives us the guarantees that we imagine. We trust, in a way, the EBS layer to do what fsync is telling us, but this is not likely the case because we know for a fact that EBS is not a simple storage drive. So a lot of the things in this design have been validated. So understanding this, we can think of different architectures. For example, instead of using remote storage like EPS, we can use local storage like the local NVMe drive on EC2 instances. And to get the redundancy that we need, we can use the database level replication. We can replicate from primary to secondaries using the native replication layer of the database. And this is actually very useful. And also, this is the basic design of many NoSQL databases, like Scylla, for example. AWS Aurora is another very interesting case. AWS also understood that that a lot of things have changed in database design, and they tried to rethink how a database should look on the cloud. So what they did is they basically split the database in two. They have one part, which is the part where you apply the log, and that part now resides on the storage nodes themselves. So we kind of get this design where the database server serves the request for read and write, but instead of writing the data to the snapshot or the data file itself, it generates the log, the commit log, which is then replicated directly to storage nodes, which apply it on the data file or snapshot. And then all of the secondaries, all they need to do is just read from that data file and serve reads. And in case of failover, you only fail the computation and the generation of the log over to the secondary. So this helps them scale better in the cloud, and also removes one layer of abstraction and makes the writes and reads and all the storage layer more coherent. Now, we have to remember when we talk about storage and the changes that happened in storage in the last 30 years, that even the API of storage doesn't make sense anymore. We basically have a block level API, which is something like, I want to write a 4 kilobyte block, and please save this block number or whatever. And reading that block is basically the same, but this makes sense when you have a disk whose physical structure basically is composed of blocks. But modern disks are not built this way. For example, SSD is more or less a key value store. It actually stores items by key, and it can utilize high parallelization, which magnetic disks did not allow for. So we kind of have a problem where we cannot use the abilities of modern hardware because we're limited by the API. Also, there's a lot of other differences. For example, you can't actually mutate data on SSD. On SSD, you can only append data, and you have an internal process of garbage collection. So this created a lot of problems. We needed to introduce a new system called trim, the famous trim, to allow the operating system to give the disk hints on how to do its internal garbage collection, and so on, and so on, and so on. So a lot of problems there, and this needed to be rethought. When we're talking about storage, we have to remember that even the storage API is not really built for today's hardware. The storage API that we currently use is a block-level API. The basic language of the API is blocks of a fixed size. And it's basically a mutable API where we write blocks in place and mutate them. And the performance for read and write is mostly the same, but there's a huge difference between random writes and sequential writes, because magnetic disks were actually pretty good at doing sequential writes. So we have a lot of operating system behavior that build on top of this, like read ahead. Also, the parallelism of magnetic disks was very, very low. But this is no longer true when we're talking about modern storage. For example, SSD is basically a key value storage device. And it has high parallelism, and it's not mutable. It has a garbage collection process instead, and basically you only append to the SSD, and there's a new system call that we introduced, the trim call, that allows the operating system to tell the SSD what it can garbage collect. But also we have virtualized storage like EBS. It's not a simple magnetic disk. It can also use high parallelization. It doesn't necessarily need read ahead. It doesn't necessarily give you higher speeds for sequential writes versus random writes. So all of this API doesn't actually make sense anymore. This introduced a lot of problems. And also there's a lot of innovative solutions for this. For example, Samsung has released a new drive, an SSD drive, that exposes a new key value store API. Of course, that's not suitable for normal usage. You need special drivers for this, but it actually gives very interesting results. If you look at Ceph, the open source distributed storage project, they have what is known as BlueStore, which is a storage layer that bypasses the file system and directly talks to storage to utilize modern hardware. So very interesting projects, very interesting cases of rethink of how to talk to new hardware. But even the operating system structure that we use in mostly all of our servers, we use Linux. Linux is originally was designed in the 90s, and it borrows heavily from Unix, which is a system that was designed in the 70s. Windows is also pretty old. It's originally from the mid-90s. Same for OSS and iOS, which are based on the BSD project from, again, the 90s. And Android, which is a fairly modern operating system, again, is based on Linux. So a lot of things have changed, and the operating system architecture has adapted, of course, but still there's a lot of gaps that, that exist. When we're talking about modern hardware, we now have multi-cores, we have a lot of cores in some cases, even hundreds of cores. We have non-volatile RAM, and operating systems make a lot of assumptions about the volatility of RAM. We have direct I/O, asynchronous I/O, which we use more and more. And the operating system struggle to adapt to this, but sometimes there's like very large gaps. Here's an example which relates to multi-core. A lot of the software that we currently use is multi-threaded, and the problem is that threads can move between cores or CPU cores, and the operating system basically decides where to locate the threads, and we can't tell the operating system, what to do. We can, to some degree, do CPU pinning, but it's fairly limited. When a thread moves from one core to another core, we have a problem. Why? Because memory is now divided into what's known as nodes. This is like NUMA nodes. And when you try to access from one core to the memory that is being owned by another core, access is slower. So the cost of it is higher, and also we need locks to synchronize the memory between threads. So this introduces a lot of performance problems and hinders our scalability. So scaling databases and other software that's multi-threaded across many cores has become a huge problem. In addition, if you have any use of the network stack itself is multi-threaded and can also relocate between cores. And we don't actually have control of this. The operating system makes decisions about where to locate the processing of packets and other network data. The operating system does its best to give you locality, both for cache and memory, but it doesn't know what your application is going to do, so it's fairly limited and it cannot solve this problem by itself. What can we do? A more modern solution is an architecture that is known as a shard per core design or thread per core design, where we have one process or one thread that's completely separate from all the other. It's a share nothing architecture. We do not share memory between threads or between processes, and each of them runs on one core and exactly one core, and does not read or write to the memory of other shards or processes. Instead, when we need to communicate between threads, we do it with an explicit RPC communication mechanism across the cores, and thus we reduce the requirement for locking, and we gain scalability for many, many cores. But this, of course, makes the mechanism of thread scheduling a bit weird because we don't actually use it. So if you look at Scylla, for example, it uses a framework, open source framework we call C-Star, which is actually like a mini operating system in itself. It does the scheduling, it does the memory allocation for itself, and it basically kind of overrides a lot of the kernel mechanisms. But again, you get this modern architecture that allows you to scale very well. So what have we learned from all of those examples? We've learned that we need to rethink a lot of our design principles, and we need to understand the design rationale of the projects that we use and the systems that we use. Why? Because a lot of them are no longer true. We need to recheck our design assumptions and start from first principles. When we do that, we can find many, many interesting things that we can change and benefit from. We shouldn't take anything for granted. Even if we don't end up changing the architecture, we will still better understand the design limits and where it can fail and what we can do about it. But it's also very important to be careful. We don't want to change architecture needlessly. There's something that's often ignored, which is the value of maturity. Maturity, especially when it comes to systems like databases, is very, very hard to achieve. It takes a very, very long time. It's basically 30 years of learning that we're throwing down the drain when we change the system. we don't want to do this unless we actually gain very big strategic advantages. So by all means, rethink your architecture, rethink your designs, but only change it if there's a lot you can gain. Just don't be a hipster. Thank you.
Yeah, Avishai, that was a great talk. Thank you very much.
Thank you.
I have to admit that it's great, but then again, quite disturbing, because you actually peel down layer after layer and showing us essentially that we are under the assumption that we're running on the top notch and the cutting edge, bleeding edge, but then again we're based on layers that have been written in the 70s or 90s and hardly equipped to to handle the new workload.
Well, as I get older, I realize that actually, legacy is not so bad,
Which is yet another disturbing thing, because on the one hand, we may think, okay, what can we do better? But then again, you bring up a valid point, which is, okay, it may be old, but then again, it comes with a lot of maturity in the software. So maybe if we, looking at the example of Hadoop that you gave, 10 years to popularize, and by then it's become outdated due to the technological changes, and also the rate is only pacing up. So how can we choose wisely the platform to adopt? As an end organization, not someone now designing a new platform like Scylla maybe, but as an end user wanting to choose the right platforms to adopt in the organization in light of these rates of change, especially in the open source domain?
I think it's not so much important to choose correctly as much as it is important to prepare for change. Because you have to assume that you're not going to get it right. There's almost no way. Even if you look into the future and you extrapolate and say, okay, in 10 years, we're going to have a machine with this many cores and whatever, a lot of things can happen in the meantime that will take it to a different direction. So it's kind of like, you can try very hard to make the right choice. Odds are you're not going to make it. But if you invest in APIs and good abstraction layers that actually allow you to make those changes later on, then you can adapt and maybe kind of shave off this technical debt. So that's one thing. And we're actually getting much better at this. One of the problems of 30 years ago is that we didn't have those kind of protocols and everything was coupled. So I used to work on mainframes a long time ago. And the problem with mainframes is that they talked directly with the hardware. So if you needed to change the hardware, you had to write an emulator because there wasn't no drivers or anything like that. So we don't do this mistake anymore. We actually have drivers and protocols and APIs. So it makes it easier, but also the APIs sometimes get older. So it's kind of work in progress. But just don't try to get it right, I guess, is my advice.
Actually, I think that's a very interesting point you made, because there was some advantage, back in the mainframe days, that everything was vertically optimized, because on the one hand, there was the disadvantage of coupling, but then again, you knew that things were like through all the different layers were very much optimized, where here you actually show that we were working on top of so many layers of virtualizations that aren't necessarily optimized to one another. The storage drivers, the virtual networks, the operating system, the virtual machine containers, and you name it. So I'm just wondering, given this state of where we stand with IT, does it make more sense to, almost also performance-wise, to use a cloud provider that is focused on optimizing the stack virtually, so the equivalent of the mainframe on the cloud arena?
So you raise a very good point. It's a basic trade-off between flexibility and performance or optimization and efficiency. And there's really no way around this. I mean, every abstraction has its cost. And actually, if you look at the way modern stack is built, we actually use sometimes 3 or 4 layers of virtualization. For example, you have sandboxes, usually in Node.js or Java, and then you have containers, and then you have the hypervisor, and sometimes like another one under that. So this is the price we pay for having the amazing flexibility we have today. But as it turns out, in many cases, you don't actually need this kind of extreme performance. Maybe you need performance, but the thing about performance is it has to be good enough. And yeah, in some cases, and this is like very contextual, you do actually need to have extreme performance. And then you see things like real-time operating systems that work directly with the hardware, and you write in kernel space. You don't use this user space, kernel space separation. So it's very contextual. I think for the most case, like the 99% of us prefer flexibility over extreme performance, and then you have 1% of the world which actually want extreme performance and don't want to pay in flexibility. So that's a trade-off, basically.
Yeah, interesting. And what would you say is the the next, as much as we can be foresee now that we're at the end of 2020 and everyone is giving predictions to 2020 to 2021, what do you foresee is the next step in the evolution in these domains?
So it's hard to say, but you do see a couple of trends that are already happening right now. So first of all, in the first time in about 20 years, the processor wars are back. Yay! If you remember, like AMD versus Intel versus Citrix, and competing architectures, RISC and CISC and all that. I kind of forgot that this happened, and then now this year, it's back. Now we have ARM versus Intel, and there's another open standard for instruction set. So this is going to be hot. There's a lot of incentives and a lot of benefits to moving back to RISC. So I think we're going to see a lot of changes in processor world for sure, and memory, and all of those buses. Also storage, I think, is going to be a big one. And then on the top of the stack, we're going to see a lot of changes, I think, in virtualization and containerization and sandboxing. I think we're going to move up a little bit. We're going to go back to runtime sandboxes. So if we actually had this 10, 15 years ago with Java, but didn't really take because it was probably too early. But now with WebAssembly, I think it's going to be back. Because it actually makes more sense if you're providing a Lambda-like service. It actually makes more sense to build around WebAssembly than it does to build around Docker containers and their API. So I think like 5 years into the future, I think WebAssembly is going to be the thing.
That's interesting. Thanks a lot, Avishai. That was a great talk. And for all our listeners, Avishai is still with us. So if you have more questions that you want to fire at Avishai, then go ahead on Discord, and I'm sure that the discussion will carry on there. Thanks a lot, Avishai, for joining us.
Bye, it was fun.